Let's take a look at solving this system of equations by graphing. The first equation, y equal negative x plus 6, is easily graphed using its intercepts. Let's let x equal 0 and find the y-intercept, which is 6. So we plot the point 0, 6. Let's let y equal 0 and find the x-intercept. Adding x to both sides of the equation, we see that x is 6. So we're plotting the point 6, 0. So we plot the y-intercept and then the x-intercept and draw a line between the 2 points. And we see that we now have y equal negative x plus 6 graphed. Now let's look at y equals 3x plus 2. First, let's plot the y-intercept, 0, 2. The constant tells me the y-intercept, the constant 2. Now let's look at the slope, 3 over 1, 3, which is 3 over 1, and that tells me to move 3 units up and 1 unit right from the y-intercept to get a second point on the line. And I actually wind up at the point of intersection of the 2 lines. So I see then that the coordinates of the point of intersection, 1, 5, is the solution to the system. And I can check to see if x is 1 and y is 5, the first equation is true, and so is the second one. Let's take a look at this next system, and let's also solve it by graphing. So let's graph 3x minus 4y equals 2. Let's solve for y. So we'll add 4y to both sides of the equation. We obtain 3x equals 2 plus 4y plus 2. We can add in any order. Let's subtract 2 from both sides. 3x minus 2 equals 4y. And now let's divide both sides of the equation by 4. And we have 3x minus 2 over 4 equals y. So we want to carefully choose our x's so that 3x minus 2 is divisible by 4. So let's let x equal 2. And we get 6 minus 2 over 4, which is 4 over 4, which is 1. So we're going to plot the point 2, 1. Let's let x equal to negative 2. Since 2 gave us a result divisible by 4 in the numerators, negative 2 will also. So 3 times negative 2 minus 2 gives me negative 8 over 4, which equals to, so my y is negative 2, so I'm plotting the point negative 2, negative 2. Draw a line through those 2 points. And there I've graphed the first equation. Now let's look at graphing the second equation, x equal 3y minus 1. And we'll simply choose our y and find the x that goes with it. So if y is 0, x is 3 times 0 minus 1, x is minus 1. So I'll plot the point minus 1, 0. Let's pick y equal to 2, and x is 3 times 2 minus 1, which is 5. So we'll be plotting the point 5, 2. So we'll plot those 2 points and draw a line through them. And when we do that, we see that we do have a point of intersection whose coordinates are 2, 1. So this system has one and only one solution, and that is the point 2, 1. So my solution is this point. Here in the first problem, my solution was the point 1, 5. If I want to write the solution set, that's the set containing the ordered pair 1, 5 for the first problem. And for the second problem, if I want to write the solution set, that's the set containing the ordered pair 2, 1. Let's look at this system of equations in two variables. And we want to solve this system by the process of elimination, also known as the addition method. If the system is dependent or inconsistent, we want to state that. So I'm going to multiply equation A by -3. And what I'm looking at here is the fact that I want to eliminate y. So I'll get a positive 18 as the coefficient of y in the first equation. And then if I elect to multiply equation B by 2, then I'll have a coefficient of -18 on y in the second equation. And when I add these equations together, the y's will be eliminated. So let's add the two equations together. And we see that 54x results when we add the x terms together. The y terms cancel out, and the constants add to 378. So 54x equals 378. If I divide both sides of that equation by 54, I get x equal to 7. So let's use equation A and the fact that x equals 7 to find y. So -10 times 7 is 70 minus 6y equals 62. Let's add 70 to both sides of the equation. And -6y equals 132. Dividing both sides of the equation by -6, y is -22. And so I have found my solution. I can actually check this by going back and making sure if x is 7 and y equals -22, both equations are made true. So my solution set contains the ordered pair 7, -22. All right, here I have a system of three equations. I'm going to look carefully at the terms, and I'll notice that the two x terms in the first two equations add to give the x term in the third. Similarly, the two y terms in the first two add to give the y term in the second equation, and the two z terms in the first two equations add to give the z term in the third equation. So this is a special situation. So I see if I multiply -1 times equation A and -1 times equation B and add that to equation C, just want to check that you have multiplied as indicated. Very easy to mess up on just the multiplication. Notice I've involved all three of the equations. I'm going to actually add negative a to negative b to c, and I see that the entire left side of the equation adds to 0, and the entire right side adds to 0. This is a true statement. So I have an equation with no variables in it that's true. That means the system is dependent. The variables have dropped out of the problem and a true equation results. The system is dependent. One of the things we want to talk about is what do the solutions look like to this dependent system. So we actually are able to see that if I multiply equation A by 8/3, I get equation C. And if I multiply equation B by 8/5, I get equation C. Well, these two, so in other words, if there are constants I can multiply two of the equations by to get the third equation, then that basically tells me that the three equations represent the same plane. The graph of a linear equation in three variables is actually a plane in space. And notice that all three equations represent the same plane. Now, this isn't always true for every dependent system, but it is true here. Each equation represents the same plane. So the solution set can be described as a collection of ordered triples x, y, z such that, and I can take any one of the equations, and this is only in the case where all three equations represent the same plane, and I can write just one of the equations. So in order for an xyz to satisfy this system, they have to make the equation 3x plus 6y plus 9z equal 12 true.